Go ahead.
Yeah, so I wanted to thank all the organizers for giving me the opportunity to hold this talk. I just want to double check, can everybody hear me? Okay, perfect. So as was mentioned before, today I'm going to be talking to you about approximate linearly ordered hypergraph coloring. First, by manner of introduction, I'm going to talk a bit about promise problems, and in particular, one of the problems that inspire this line of research, which is the approximate graph coloring problem. In this problem, I give you a graph, and I promise, hence promise problem, I promise that the graph is three colorable, like this graph. But I don't give you the coloring, and then I ask you to find a coloring with a larger number of colors. So this is easier to do in principle. If I counted the colors here correctly, there are 5 colors, but you never know. So again, I give you a 3 colorable graph. I don't tell you the coloring, and I ask you to find a 5 coloring. And we can ask various things about this problem. Is it hard? Is it easy? It can't be harder than doing 3 coloring, but it might be easier in principle. Well, in this case, it isn't, because this was proved just 2 years ago. For 3 coloring versus 5 coloring, it's NP hard. But on the other hand, for 3 versus 6 coloring, nobody knows yet. It's still open. So 3 versus 5 is hard, 3 versus 6, open. There are some conditional results that are known with the D2-1 conjecture and so on, but really 3 versus 6, and for 3 versus any larger constant, it's open. So this is sort of one of the bounds, the hardness bound. What is the smallest number of colors that we could use to color the graph? So if I give you a 3 colorable graph, again, without giving you the coloring, what's the smallest number of colors that you can get away with and color my graph? Well, even in 1983, Wigderson gave an algorithm that uses only O of square root of n colors. So again, you notice this is a non-constant number. It depends on the number of vertices, n. And this has been improved step by step for the last 40 years almost, up to today, where the state of the art by Kawarabayashi and Thorup gives O of n to the 0.19996 coloring for a 3 colorable graph. Now, this constant looks really random, but it's actually a very big improvement from the last one, because up till this constant, people kind of thought that maybe 0.2, so the 5th root of n, is a natural bound. But it's just a bit below 0.2, so who knows where the bound is. So this is the approximate graph coloring problem, which again is the main inspiration for this line of research. Instead of looking at graph coloring, which is probably difficult to, shorten the gap, we're going to look at this different notion of coloring called linearly ordered coloring that was first introduced in the context of promise problems in this paper BBB, Barto, Battistelli, and Berg, just 3 years ago. So what is a linearly ordered or LO coloring? Suppose I give you a 3 uniform hypergraph. This means that every edge contains exactly 3 vertices, but it might be the case that 2 of the vertices are equal. In that case, the multiplicity matters, basically. But you have 3 vertices in each edge. A linearly ordered coloring with K colors is an assignment of these K colors that have an order on them. So you think of them as 1 to K, so that for every edge, if 2 values in the edge have equal colors, the third one is larger. An equivalent way of stating this is that every edge has a unique maximum color. Here I have 3 examples, rather 1 example and 2 non-examples. Here we see you have in one edge 2, 2, and 3. This is okay. The 2 smaller things are equal, but the third thing, the 3, is larger. Here we have 2, 2, 2. All 3 of them are equal. This isn't a properly LO colored edge. Here you have 2, 2, 1. Here, the maximum isn't unique. 2 appears twice. So this isn't a proper LO coloring. And I'd like to bring your attention to this LO2 coloring special case. In such a coloring, in every edge, I have to have 1, 2, and 2 1s. So you can think of it as selecting exactly 1 vertex in every edge. So it's a 1 in 3 coloring, in a different way of stating it. So with this notion of coloring in hand, we're going to want to look again at the similar sort of approximate version of the coloring problem. So like before, if I give you a hypergraph that's colorable with a small number of colors, what's the smallest number of colors that you can actually color the hypergraph with? And today I'll be explaining an algorithm that if I give it a hypergraph that has an LO2 coloring, so a coloring that selects exactly one vertex in each edge and sets that to 2 and everything else to 1, it'll find an LO coloring with this number of colors. This is basically the cube root of n, but it's a bit better than the cube root of n by a factor of log. In the previous version, in some previous work, both also with me and my supervisor, we had an algorithm that was about square root of n. So this is better. What's our main idea in this algorithm? How are we going to create our coloring? Well, at every step, we're going to either color some subset of the hypergraph with a big color or with a small color. And then we're going to continue recursively in such a way that we can always be guaranteed that the edges are colored properly. So in the case of the big color, we're going to color an independent set with the big color. In this way, all the edges that touch the color we use are going to be correctly colored, since the big color is the unique maximum in that edge. In the case that we color with a small color, we're going to want to color a subset of vertices that intersects each edge in exactly 0 or 2 vertices. Why is the case? If I intersect in 0, then I'm going to color the edge recursively. If I intersect in 2, then I have that edge. The two of the vertices have an equal value, that's small, but the third value is going to be strictly larger since we color with this small color. And then again, everything later on was going to use a bigger color. Our goal in general is to always find one of these two kinds of sets. So either an independent set or a set of vertices that intersects each edge in 0 to vertices with omega of n over f of n vertices. For reasonable values of f of n, like the one I'm going to use in this proof, this means we'll be able to get an LO coloring with f of n colors, all of f of n colors, just by recursively applying this thing over and over again. Okay. How are we going to actually find these sets? Well, we have two cases, and it really depends on the density of the graph. So if I have more of, at most, O of n times delta edges, and this delta is a parameter that we're going to fix later on, so as to optimize our algorithm, then if you think about it, I have a sparse hypergraph. It should be easy to find an independent set, and it is. We can find an independent set of size n log n over delta log n. Great. If, on the other hand, I have asymptotically more than n times delta edges, it turns out, and this is, I think, the more interesting side, you can find a set that intersects each edge in 0 or 2 positions, which was the other case. This is the case where we color with a small color. Then setting delta to be, setting it properly, basically to make these two expressions equal, we get exactly the result we want. We get the minimum number of colors that we want. Okay, let's consider the first case. Case 1, which is the light case, the sparse case. Let's consider only something I'm going to call light vertices. These are vertices with degree bounded by O of delta. And let V prime E prime be the hypergraph induced by this subset of light vertices. I have here two facts. First of all, this sub-hypergraph has size omega of n, so like n over 3, let's say, or something like this. Second, the sub-hypergraph also has an independent set of size, the number of edges over delta. The first fact is kind of not difficult to see. Basically, if the light hypergraph is too small, then there are many heavy edges. So edges with more than delta, asymptotically more than delta, vertices with degree asymptotically bigger than delta, which means that our graph can't have O of n delta edges. Basically, there's too many. For the second fact, we want to show that our sub-hypergraph has a big independent set. Well, remember that as my promise, I'm promised that my hypergraph as a whole has an LO2 coloring, which means the induced sub-hypergraph also must have an LO2 coloring. So this V prime E prime has an LO2 coloring. If you remember, a different way of describing this LO2 coloring is that in each edge, I select exactly 1, 2, which means that the 2's in this LO2 coloring form an independent set. Each edge contains 1, 2, and every 2 can be shared among delta edges. Each edge contains 1, 2 because that's what an LO2 coloring is, and each 2 is shared among delta edges because that's the maximum degree. So just by these facts combined, they're at least size of E prime over delta 2s, which is the size of my independent set. Now, this means we basically have a pretty big independent set in my subhypergraph. Can we find it? It turns out we can, because by a theorem from Haldarsson in 2000, if I give you a graph that has an independent set of size S, an average degree D, you can find an independent set of size S log D over D log D. Also, pretty easily, if we have average degree D, you can also get an independent set of size omega n over D. This is needed for a special case, but I won't get into it very much. By applying these algorithms to our hypergraph, not really our hypergraph, rather to the primal graph of the hypergraph, which is what happens when you replace each edge with a triangle, we can get an independent set of the required size. Basically, this S, if you replace it with this E prime over delta, it gives you exactly what we want. So in this case, we do some analysis, we can find a big independent set with this algorithm that uses semi-definite programming. Next, we have this case for linear hypergraphs. Sorry, in order to discuss case 2, I first need to explain what a linear hypergraph is. If I give you a 3-uniform hypergraph, I say that it's linear if and only if, for any 2 edges, they intersect in at most 1 vertex. This basically means that this configuration is forbidden. So I can't have 2 edges that overlap on one of their sides, basically. How does this help us? Let's suppose that our hypergraph is not linear. Then in my LO2 coloring, the vertices that are not in common must have the same value. Why? If I consider there are only 2 cases, if the common vertices have values 1 and 1, then the not common ones have to have value 2. If the common vertices have value 1 and 2, the not common ones have to have value 1 and 1. This means that I can identify the not common vertices as long as my hypergraph is not linear, and I maintain the property of being LO2 colorable. And in fact, once I then find an LO coloring with a bunch of colors, I can just undo these identifications and get an LO coloring for the original graph. By doing this, I can assume my hypergraph is always linear. Why do I care about this? Well, let's consider some linear 3-uniform hypergraph that admits an LO2 coloring. For instance, this one. Now, let's look at only the 1 vertices, like this, basically. You can see that the 1 vertices form a subgraph of some sort, where each edge between them corresponds to one of the triangles in the original hypergraph, and you cannot get multiple edges. Why? Because of linearity. Multiple edges would immediately give you a pair of edges in the original hypergraph that share 2 vertices. And furthermore, every edge in the original hypergraph corresponds to an edge in this graph. Now, let's use this fact. So, by this fact, we can deduce that if I have a linear 3-uniform hypergraph, then, and it admits a LO2 coloring, it also admits an LO2 coloring with square root of the size of E, square root of the number of edges, vertices colored with the number 1. Why? Well, as we saw before, if I just consider the vertices that are colored with 1, I can construct this graph with the same number of edges as the original hypergraph that doesn't have multiple edges. Because of this, I have to have at least square root of E vertices. Otherwise, I can't get a graph with this many edges. Okay. Now, you'll notice that the vertices with value 1 are precisely a set of the type I want. The vertices colored with 1 intersect each edge in exactly 2 places. So in particular, they also intersect each edge in 0 or 2 places. Now that I find that, so now in our case, where we have omega of n delta edges and the input graph is assumed to be linear, I have a set of size omega square root n delta that intersects each edge in 0 or 2 places, the one I just constructed. Can I find it? It turns out I can find this as well with another algorithm from the 2000s that uses semi-definite programming. It looks a bit different. What it says is that if I give you a system of modulo 2 linear equations, I can maximize the number of ones in these modulo 2 linear equations up to a constant factor. And I'll explain why this is exactly what I want in just a sec. Suppose that I have an edge XYZ. I want to select 0 or 2 of them, but this is the same thing as saying x plus y plus z is 0 mod 2. I want to maximize the number of ones. I want to maximize the size of my set. It's exactly the same. Okay, so I can find, in this case, what I want. So now putting all of these things together, how does our algorithm look like? First, we have this pre-processing step. If our input hypergraph is not linear, I make it linear by identifying vertices. And at the end, I'm going to undo these identifications. If my graph is sparse, I have O of n delta edges, then I can find a big independent set, big enough for our purposes. If our hypergraph is dense, then I can find a big set that intersects each edge in 0 or 2 places. And in both of these cases, I color either with a large color in the case of the independent set or a small color in this case. And then I just recursively color everything else. And if you just do a simple application of the master theorem with this delta value, it gives you that this is the number of colors you use, which again, it's asymptotic improvement from about square root of n to about cube root of n. So I was quite happy with it. Let's go through a quick example. We see here a hypergraph. It admits an LO2 coloring, as you can see. Let's say we don't know the LO2 coloring, of course. Now, first, let's suppose that this graph is dense. In this case, I want to find a set that intersects each edge in 0 or 2 places. Let's say I have this set. I color it with ones. Now, let's say the graph is sparse. I want to find a big independent set, and somehow I get this independent set of just one vertex. It's fine. And then I just have these 4 vertices. The graph is sparse. I get an independent set. Everything is independent. So I color it all with 2. And now I have an LO3 coloring of the hypergraph. And this actually leads me into some interesting open questions. So if you remember in the case of graph coloring, we know that 3 versus 5 graph coloring is NP hard. For linearly ordered coloring, even LO2 versus LO3 coloring, we don't know if it's hard or not. So this is basically what happened here. I had an LO2 coloring, I get an LO3 coloring. We don't know if it's NP hard or not. And this is actually why this problem was interesting to me. In that paper that introduced it in the promise setting, this was the only problem in this big class of problems they couldn't classify. So I think there's something interesting happening here, and it's worth further study. So this will be one side of it. Can we find any hard results at all, even 2 versus 3? 2 versus 2 is just known to be hard anyway. On the other hand, there's also this positive side to the work. Can we find an LO coloring with fewer than about cube root of n colors? I'll be very interested if anybody could do this. Anyway, that's more or less everything I wanted to say. Sorry if I went too long or too little.
All right, let's thank the speaker. Questions? We have lots of time for questions.
Oh, it was very clear. It's not a question. It's just I don't have questions because of that.
I'm happy to hear it was clear.
So how many papers are we going to write on this? What do you think the bound is?
Well, at the moment, there's the ICAP and the journal version. I'm taking a break on this problem. I'd like to think about it some more later. I'm now doing some other more complexity kinds of stuff. So more hardness results, but I thought this result would be nicer to present basically because it's an algorithm.
Right. But yeah, so 1/3, I mean, cube root of 3 might not be the right bound, but you have no intuition of how to improve this. Or
At the moment, I really don't. So this
Okay.
algorithm is really natural in some sense because you have this min-max thing. You either color small or big, and it makes sense somehow. Those are the only two natural places where to color, right? Maybe some more kinds of ideas from Karabashi, Thorup, or KMS. There are all these. I think KMS are the authors of this other paper. There's SDP for graph coloring, for approximate graph coloring. There are all these ideas for approximate graph coloring that may be applicable here.
Mhm. Okay, very nice.
So this is a comment that Tamio sort of already knows because we chatted about it last year in Paris, but maybe some of the people that are doing graph theory would be interested. I was talking